Welcome back, everybody. So today we'll be working with working on lecture 1B on introduction to sets. So in this topic, we'll be interested in studying the relationship between collections of objects. And the first thing we really need to define is what a set is and what the things inside of them look like. And this is really just a sophisticated way to talk about a collection of objects. And we'll talk about what the notation here would look like. But the things inside of a set, the objects in a set, are called the elements of a set. Okay, so we're going to start off with some examples and talk about different ways that we can write the same exact set, but the ways that we'll write them kind of in the most the simplest ways to really ultimately be able to count them. That's going to be our end goal, is to be able to count these sets because that'll help us with our probability section. Okay, so the set of all possible outcomes of rolling a six-sided die, we're going to label the set to be capital A. Usually with our sets, we'll use capital letters to label them instead of writing out the full set every time. And then we usually use lowercase letters for the elements of, but here we'll actually write out the specific elements that we have. And with all of our sets, we're going to start out with drawing our curly brackets to tell us that we're starting the set. We'll list out all our elements, and then we'll close out our set by closing the curly bracket here. So the set of all possible outcomes of rolling a six-sided die are the numbers 1, 2, 3, 4, 5, and 6. But something that we'll notice is that order doesn't matter. So this is saying if I had written my set in a different order, I'm really representing the same exact objects. Really, my order does not matter here. Something else that we'll notice is that repetition doesn't matter. So if I write the same object here in this instance as 1 twice or more than once, I really have that object in my set once. I've just written it twice. So really, I want to write my sets in the most simplified version so that the only things that are listed are unique objects. So I don't have repetition in here. That way it's a lot easier for me to decide how many elements do I actually have. And in this case, it's a little bit harder to decide because I have that repetition here. Although technically, if I do repeat the same element, it is the same set. So repetition and order don't actually matter, but we're going to write them in the most simplified version to make it easy for us. And most of the time, if we're working with numbers, I'm going to list them in increasing order just to keep it more organized. But again, the order does not matter. And that one matters even less, right? If I wrote it 6, 5, 4, 3, 2, 1, or all jumbled up, really the repetition is what we don't want to do to keep it as simplified as possible. Okay, so we want to be able to symbolically write when we have elements inside a set so that we don't have to use quite as many words. So here we see that 2 is one of the outcomes of a six-sided die, rolling a six-sided die. So it's an element of our set A. Okay, so here the way that we would write this in symbols is 2 is an element of A. So here this symbol we'll literally read it as an element of, or we can say in. 2 is in A, inside the set. Okay, if we want to say that something is not in the set, in this case, we would be saying that something is not an outcome of rolling the six-sided die. So in particular, 7 is not an outcome, so 7 is not in the set. It'll look very similar, but instead of saying an element of, we're going to say not an element of, and we'll put a slash through it. So here, when I use this symbol here, I literally mean not an element of or not in. Okay, so again, what we want to be able to do is to count our sets. So what we call this, the number of elements inside of a set, the number of really unique elements inside the set, is called the cardinality of the set. And it's going to be denoted with our absolute value symbols, right? So around my set, if I have my set S, I'll put these absolute value symbols around it to represent the number of elements inside of them, or sometimes we might say the size of S, right? Cardinality, or the size of S, really is telling us how many unique elements we have inside of our set. Okay, so here we have our set 1, 2, 3, 4, 5, 6. And we can see that the cardinality of this set is going to be 6 because we started with 1 and I didn't have any repeats and I really went through all my numbers up to 6. I can see that I have exactly 6 elements here. That won't always be the case. Maybe I'll start at 0, maybe I'll start at 2, maybe I'll skip some elements and then I actually have to do some counting. But here, because I'm starting at 1, I don't skip, I don't have any repeats. It's easy for me to count my set here. Okay, and let's think about the set of outcomes from rolling a 12-sided die instead. So we're going to say B is the set of elements 1, 2, 3, 4, 5, 6, 7, and I don't want to write every single element. So as soon as I see some pattern showing up, I'll put these ... dots, and I'll tell you where I end. And so this really means all of the elements, all of the numbers, all the whole numbers, 1 up to 12 here. And I can see that the number of elements, or the cardinality of B, is going to be exactly 12. Even though I didn't list out all of my elements here. Lots of times we're going to be working with big sets. So if we can see a pattern showing up, we'll use these ... dots to help us write them a little bit faster. But something that you'll notice in this example that we're working with is that every element of A, all of the possible outcomes in a 6-sided die, is also an outcome of a rolling a 12-sided die. So it's also in B. Okay, when this happens, we have a special name for this. We say that A is a subset. So it's a smaller set living inside of B. And the way that we write this is using the following symbol with this C that's really like a short C with a line underneath to really say subset. That line underneath is really saying that possibly they could be equal as sets. They could have the exact same elements. But we just have enough information to say that that A is a subset of B. All the elements of A are also elements of B. So in words, the way we would say this is a subset of. Okay. What we'll also do is draw what are called Venn diagrams. So we'll draw our sets and we'll talk about how they interact with each other. In this case, if I had my set B here, if A is a subset of B, it's going to lie entirely inside of it. Right, and these could be blobs, but really most of the times when we're drawing our Venn diagrams or our sets, we're going to use circles. Oop. And so here, if this is my set B, I want my set for A, my circle for A, to lie completely inside of it. Okay. So let's look at this next example. The set of people in Oregon, we'll denote it by this big O, is a subset of the set of people in the West Coast of the US. So in symbols, we write this as this big O is a subset of this W, which represents the set of all people on the West Coast. But I could keep going. There are bigger sets that these are all a part of, right? The people on the West Coast are also in the US. So I can symbolize the set of all people in the US as U.S. Dot here. And I could really keep going. I could find bigger sets of where all the people in the US are a part of, maybe the Northern Hemisphere, the Western Hemisphere, things like that. People on Earth, I could keep going and keep going. But really, in most of my situations, I want to know, where do I stop? Where can I think this is the biggest set that I'm working with in this context? These are the only elements I really care about. Okay, so usually when we work with sets, we define a set of all possible elements of any set used in a problem. And we're going to call this the universal set. Um, and lots of times we'll denote this with a capital U. So even if I don't tell you capital U is the universal set, I'm only going to use this capital U to represent the universal set, how far we're able to go here. So maybe let's say in our context for this example we were working with, we really only want to go up to the people on Earth versus just the people in the US. So in our example, this capital U, the universal set, will be the people on Earth. And anytime we're working with the universal set, to make it obvious that this is as far as we're going to go, these are all the outcomes that we can have represented in our sets, we're going to be using a rectangle instead. Okay, so anytime I'm working with some of these examples, I'm always going to draw my rectangle first. This is going to represent my universal set. So this is the people on Earth. Okay, and then within them, in there, I'm going to work with specific sets and decide how do they interact with each other? Do they overlap at all? How much do they overlap? Do they not overlap at all? And so here I could have the set of people in the US, and I could draw these as rectangles, as circles, as blobs, or as maybe in the shape of the states. So I could have something like the West Coast people, and then within those, I'd have people living in Oregon. I also have people outside of the US, so things like Australia can also show up here. And I really have a lot of sets, but most of the time we're going to restrict ourselves to specific ones, because here we could see that we could make this as, we could have a lot of sets showing up here for every country, for every state, for every city, right? That would take up a lot of space in here, but it depends on what we want to study within that problem. Okay, if we want to talk about elements in the universal set, which are not in a set A, then this is called our complement of A. So here, I'll use the following notation. My set A, I want the complement of it. So in the power, I'm going to write the C for complement. And these are the elements in the universal set, U, which are not in A. So anytime we talk about complement, we have to know what the universal set is first before we can actually do that. So the way that we would draw this in our Venn diagram, so in our picture, to represent this, again, we need our rectangle to represent our universal set. This is going to be my U. Everything inside of this rectangle really represents all of the elements inside of U. Okay, if I have just one set, again, usually I'm actually going to use circles. So I'm going to use my circle here to represent my A. And if I want the complement of A, I really want all of the elements in my universal set that are not an A. So everything outside of A. So the region that we're talking about here is this region outside of my set A. Right, so this portion here is my A complement. Okay, and we'll actually find a different notation to write this as well, but we'll see that in just a second. What we'll also see is so my universal set is a set itself. What if I want the complement of my universal set? Okay, this is going to be the set of elements in U, which are not in U, right? That's impossible to be in U and not in U at the same time. So I have no elements in my set. So I'm just going to close my brackets for my set. This has no elements in it. We have a nice symbol for this for our what we call our empty set. It's a set with no elements. It's the only set with no elements inside of it. It's the only set where the cardinality is exactly 0. So here we see if I take the cardinality, if I count the number of elements inside my set, there are exactly 0 in them. 0 inside my set, so the cardinality is 0. The size of my set is 0. Okay. Taking this complement, we can actually generalize a little bit more. We can take any two sets in our universal set, and we can think about what are the elements in one set that are not in the other. So here, if I had two sets, A and B, inside of my universal set, this following notation, this really like a minus sign in terms of my sets. And really we can just say minus, or you can say set minus. It's going to be the set of elements in my first set, which are not in my second. So in A, that are not in B at the same time. Okay, so here, if I draw the region that's corresponding to this set, I want the things inside of A. Okay, these are the things inside of A, but I don't want the things inside of B as well. So I need to delete this region here. So I really just want the things in A that doesn't overlap with B here. Okay, there's a different way I can write this in terms of complements. Here, oh, and actually, we'll come back to this. We don't have quite enough info here to write it in that way, but we'll come back to how we write it in a different form. But what we can do is we can think about the complement in this way, right? I want the things inside of U, which are not in A. So I want the things in U and subtract the things in A, right? So this complement I can actually write as using my set minus, but it's a special type when I know I'm starting with the universal set and taking something away. With my set minus, I can do this with any two sets in my universal set here. Okay, but we'll come back to a different way that we can notate this set minus using more symbols that we'll learn in just a second. Okay, so this is really a check-in where we want to determine whether the following statements are true or false, given U, the universal set, the set A, the set B, and the set C. And this would be a good place for you guys to pause and kind of try out these problems, decide if it's true or false, give some justification if it is false, and then come check back in with me to see if your solutions were right. If you don't feel comfortable yet, we can work together and decide what these are here. Okay, so let's look at our first statement. We want to decide true or false. Are 2 and 7 inside of A? So let's take a look. Let's look at our set A. I do have the element 2. I do have the element 7. So I do have 2 and 7 inside of A, right? Remembering A and is telling me that they both have to be true. 2 is an A and 7 is an A here. So because that and statement is true, the statement here is true. Okay, and I need to look at my next statement. 6 is not an element of B. So I need to check, do I see 6 showing up in my set B? If it is there, that statement is false. If it's not in there, then that statement is true. And here, I don't see a 6 showing up in my set. So I know that this is a true statement. Okay, I'm going to keep going. 1 is in A and 1 is in C. Let's check. 1 is in A. The statement is true. And 1 is not in C. Or if you look at our C set here, 1 is not in here. This is false. So I have my first part of my statement is true. My second part of my statement is false. And I have an and between them. So this is going to be false. And the reason behind it is because 1 is not inside of C. right? 1 in C was a false statement. Okay, so this is where we're seeing our ands, our ors, going to be showing up here. And we're actually going to be able to talk about combining sets using these ands and ors in some way. Okay, so let's see. 7 is in B or 7 is in C. Let's see if that's true. 7 is in B is not true. 7 is in C. It is in there. This is true. And because this is an or statement, if at least one of them is true, then the whole statement is true. So here I can give some justification since 7 is in C, which is enough for my or statement. Okay, let's look at our next one. The cardinality of A, or the number of elements, the size of A, is equal to 9. And let's check. This one is a little bit different. Here I'm seeing I'm starting at 0 and I'm ending at 9, and it doesn't look like I've missed any elements. So I don't have 9 elements in here. I actually have 10. If I started with 1 and went up to 9, then I would have 9 elements. But if I start at 0 and go up to 9, I have 9 plus 1 or 10 elements in here. And I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I do have 10 elements in here. And this is telling me that the statement is false. The cardinality of A is not equal to 9. It's actually equal to 10. Okay, let's look at our next one. The cardinalities of B and C are equal to each other. So we can find the cardinalities and see that they're the same number, right? Again, our cardinalities are giving numbers back out, not sets. We can decide if the statement is true or false. Here we can see the number of elements in B are 1, 2, 3, 4, 5. The number of elements in C are 1, 2, 3, 4, 5. Since they're both equal to 5, this statement is true. Okay, let's look at the next one. B is a subset of A. So this is saying all of the elements of B have to show up in A. So I'll check, is 1 inside of A? It is. Is 2 inside of A? It is. 3 is inside of A, 5 is inside of A, and 8 is inside of A. So here, this statement is true because every element I found in B can also be found in A. That's what we mean by subset of. Okay, let's check for C, a subset of B. I'm going to go through my elements in C and decide, are all of them inside of B? As soon as one of them is not, then the statement is false. Okay, let's see. Is 2 inside of B? It is. Is 3 inside of B? It is. Is 5 inside of B? It is. Is 7 inside of B? It is not inside of B. Okay, so this is enough for me to say that this is false. Since 7 is an element of C, but 7 is not an element of B. So as soon as I find an element in my first set that's not in my second, then it can't be a subset because I need all of my elements in C to be inside of B. Okay, here we have a tricky one, and this is our notation, remember, for our empty set, or our set with no elements inside of them. Okay, and here we can see that, or what we want to check is the empty set a subset of C? Okay, so they're both sets, and I want to check, are all the elements inside the empty set also in C? But let's remember there's no elements in the empty set. And so this is kind of a tricky question. This is what we call vacuously true. If there's nothing to check, right? If there's right, if really the way to show that this would be false is by finding an element in the empty set that's not in C, but that's impossible because there's no elements in the empty set. So this one is actually true, even though it feels false. And really what we can see is that the empty set is a subset of any set that we're working with vacuously, because we can't show that it's false. Okay, and let's see here. Is the empty set equal to the complement of A? So really I want to check if U is my universal set, if I take the universal set and delete all of the things that show up in A, do I have nothing left over? Okay, and there's actually a faster way for us to do this, but let's check it out. If I have 0 in A, I want to take that away from U to see if what I have left over. So I'm really going to delete all the things I see in A from U. So I'll take away 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are my elements in A. And I'll notice that I do have an element left over. So the complement of A is exactly the set containing 10, which is not equal to the empty set because it has an element inside of it. So this is false. The only way that we're going to get that a complement is equal to the empty set is if we're working with a full universal set to begin with, but A and the universal set are not equal because it doesn't have that element 10 in it. Okay, but these last two were definitely a little bit trickier, but if you understand all the ones before it, those are really the more important ones here. Okay, so we're going to talk about how we can combine sets in different ways. Right, we saw previously we can delete elements from sets. And what we can also do is look at what do they have in common, what is the overlap, and we can also just combine all the elements together. Those are going to be the two ways that we're going to make a new set given two sets here. So given two sets A and B, we can build other sets. The first one being the intersection of the sets. And here we're going to use the following notation for the intersection of A and B. So I'll have my set A and B, and in between it, I'm going to put the intersection, right? But really when I read this, I'm going to say A intersect B. Okay? This is going to be the set of elements. That's all the elements in A and B at the same time. So really I want to think at the same time. So really what I need is that I want elements that are in A, and that same element has to be in B. So it has to be true for both of those statements there. This one is really working like our and, which we use the caret facing upward to represent that in our logic. In our sets, we're going to use this more rounded like an upside down U, or you can think of this like as an N for intersection. And we really want to think about what does this look like in our Venn diagram. Okay, so here I want the elements that are in A. So I'll start with those elements. Okay, but at the same time, I want the elements to be in B. So I'll notice that these elements here are not in B, so I don't want them in there. So these are the elements that I'm left over with. This is the intersection. This is really the overlap between A and B, what they have in common. So this is our intersect. You can think and. You can think overlap. Or the commonality. Whichever way will make it easier for you to remember. But in symbols, this is A intersect B. Okay. So let's look at a couple examples where we actually try to find the intersection given the sets. So here, what I need to do is I need to decide what elements do A and B have in common, which ones are showing up in both of my sets. Okay, so here I'm going to run through my elements in A, and I'm going to decide, are those elements inside of B as well? So I'll see 1 is not in B, so it's not going to be an intersection. 2 is not in B, so it's not in the intersection. 3 is in B, so I'm going to draw that in my intersection. 4 is in B. Oh, this should have been a 3, excuse me. So I'll have 3 and 4. I'll have, next I have 5, which is an A and it's in B. Then I have 6, which is an A and is in B. And I can technically stop here, right? Because these are all the things in A that were also in B. But I can also check the thing that I have left over here, the 7, is not an A, so it's not going to be in the intersection. Okay, so this is my intersection of my two sets. And I'm going to look at my next example, and I'm going to decide which elements do they have in common. So here I can look at A. A is not in B, so it won't be in my intersection. I'll look at little b. Little b is not in big B, so it's not in my intersection. And I have little c. That's not in big B, So it's not in my intersection. And really, I know I can close it out here, but I can just check just to make sure the things in E, or excuse me, the things in B that are not in A, or B, the things in B are also not in A, so it shouldn't be in the intersection. So E is not an A, F is not an A, and G is not an A. And so my intersection is empty. This is my empty set. This is telling me they have nothing in common with each other. So when this happens, this is actually really important. When two sets don't share any common elements, so this is a fancy way of saying the intersection of the two sets gives us back the empty set, right? That's what it means to have nothing in common in terms of sets. Then we call these sets mutually exclusive. And let's actually go back and let's think about what does it mean in terms of our Venn diagram for our sets to be mutually exclusive. So when A intersect B gives us back the empty set, we can actually say more in our Venn diagram. Here I have my set A. And what I want is that the intersection or the overlap, what we have in purple here, that is the empty set. There's nothing in that set, so that they have nothing in common. This really means that I can draw my two sets separately. And here we see that there's no overlap at all, right? So they're completely disjoint from each other. They're completely separated. They have nothing in common. And so anything in A won't show up in B. Anything in B won't show up in A. Okay, so this actually gives us just enough to be able to write our set minus in terms of our intersection and our complements. So here, where I had the things in A that are not in B, what I can say is I want things in A, and at the same time, I want it to not be in B. Okay, so when I say and, just like in my logic words, or in my logic section, this is representing my intersection in terms of my sets. So I say A and I want it to not be in B. This is my complement. My complement is really working as my not from my logic section here. So if I want the things in A that are not in B or A minus B, this is A intersect B complement. So this just gives us another way for us to write the set minus, although it's much more convenient to write this set minus notation instead. Alrighty. So we have one more way that we can make a new set out of two other sets, and this is just by combining all the elements together. This is going to be called our union. This is actually the easiest one. There's a lot less work to have to do to decide what the union is. And this is going to work as our OR. So if it's in at least one, it's inside of the union. Okay, so this is going to be the set A, union B. So here for my union, I'll have this big U to represent my union. And these are going to be the elements, all the elements in A or B, where this is that same OR we were working with before. This is our inclusive OR. So we can, so the elements can be in both. It doesn't just have to be in one at a time. Okay, so if I have my set A and my set B here, what I want to do is I want to include the elements inside of A and the elements that show up in B as well. Because all I need is that my elements show up in at least one of them. And that's enough for my OR statement to be true. So that's enough for it to be inside of my union here. So for my A union B, this is really my nicest one. It's going to be the combination of my A and my B here. So I just combine them both. Regardless if they overlap or don't overlap, I just take all the elements in A, list them out, and then add the elements in B, and that'll give me my union back. So here, I'll take my elements in A, 1, 2, 3, 4, and then I'll combine it with my elements in B. But we'll notice, if I do this, I'll have a lot of repetition, and I really want to write this as condensedly as possible. So I can see, I can also write this as 1, 2, 3, 4, A, B, C, because this 3, 4 was already accounted for. I don't want to write it twice just so that I don't confuse it in thinking that I have more elements than I actually have here. Okay, but again, this is working like our OR, right? Our intersection, or the one that looks like an N, is the overlap, which works like our AND. It has to be in both at the same time. Our union, or our U here, is going to be combining them together. It's going to be like our OR. It has to be in at least one of them to be in the union. Okay, so our goal is to be able to count our sets. And so one thing that we want to be able to count is the number of elements inside of our union using information about the size of A, the size of B, and the intersection. We can actually do this. So the way that we go about this is by adding the number of elements in A to the number of elements in B. But what we need to be careful about is when we did this, and actually that's what we did here. We added all our elements in A, and then we added all the elements in B. We're actually overcounting when our A and B have things in common, right? Another way I can think of this is, let's say I count all the elements inside of A, and I add this to all the elements inside of B. We'll notice that we overcounted. We counted this middle section 2 times, which is too many, right? So here we have to subtract the overlap that we counted twice, and we only want to count once. Okay, so here what we can say is, if I want to count the size of my union, the size of the union of A and B here, I'm going to take the size of A, or the cardinality of A, add it to the size of B, and then subtract the overlap, subtract what they have in common, which is exactly the intersection here. Okay, and we can actually do something else. We can actually manipulate this equation by moving this guy to the left and moving this guy to the right. We can actually get an equation to tell us what the intersection looks like in terms of the size of A, the size of B, in terms of the size of the union. So they'll look very similar. So the size of the intersection, I can count by adding up the elements in A to the elements of B, and then taking away the elements inside of the union here. Okay, and these will be really handy to us in our counting section and in our probability section. So we really want to feel comfortable being able to use these, and we'll see these showing up later in our worksheet. Okay, so let's do some practice. And again, this would be a good spot for you to try out these problems, pause the video and come back in and check your work. But I'll go through these. Okay, so here I want to find the intersection of A and B. So I'm going to see, what do they have in common? And again, I always need my curly brackets for my sets. I'm not just listing my elements. I want the set of all these elements. And I want to see, what do they have in common? Not A, it does have B, it does not have D, it does have E, and it does have F. Okay, so that's enough. I don't have to go check in B. I can just check, what are the things in A that are also in B? So I'll get B, comma, E, comma, F. Oh. Okay, and next up, we have the complement of the set. So it's unlikely that I'll ask you for the complement of something complicated. I'll usually ask you for something, for what I want the complement of first up here, and then I'll ask you to take the complement, because it's much easier for us to do this versus just trying to find the complement of the intersection instead all the way through. So here my goal, and what I'm seeing show up here, is that this is the same set as this one here. So I really want the complement of the set. So I really want to check inside my universal set. I want the things in U that are not in this set. So I can really delete them from my universal set, B, E, and F. And whatever I'm left over with is going to give me my complement here. So I'll have A, C, D, G, H, I, all the things that I did not delete. And one thing that we'll notice is if we add up the size of a set plus the size of the complement, because they have nothing in common and they make up the whole universal set, it should give me the total in my universal set. So here I have 3 elements. Here I have 6 elements. And if I check, I do have a total of 9 elements coming from U. And this is a good sanity check. Did I make sure to delete all the things? Did I not repeat things by accident? Because a set and its complement should have nothing in common. Okay, let's look at our next 2 here. Next up, we're going to be finding the complement of a union. So first we'll find the union itself to make it easier. And really the unions are our nicest. I'm going to take everything inside of A, and then I'm going to add the things inside of B because this union is an OR. If it's an at least one, it's going to be in my union. And so I'm going to see which things am I missing. I already wrote B, so I'm not going to rewrite that one again. I'm missing C. I already wrote E. I already wrote F, and I'm missing G. And if you wanted, you could write these in alphabetical order to make it more obvious what we have going on. So I have A, B, C, D, E, F, and G. Okay, so I have 3, 4, 5, 6, 7 elements here. This is telling me in my complement, I should only have 2 elements because altogether I should get my universal set back out. But I can do my same trick as before. I'll delete all the elements inside this union from my universal set. So I'll delete A, B, C, D, E, F, G, and all I'm left with is H and I, which is good. I only wanted 2 elements because in total I should have 9 in my universal set here. Okay, let's do something a little bit more complicated where we're given a bunch of information and our goal is to draw the Venn diagram. And within the Venn diagram, we want to say how many elements do we actually have in that specific region. Okay, so the first thing I'll do is I'll draw my Venn diagram. And then in a second, we'll decide how many sets should we have included in here and how do we count the sizes of these sets here. Okay, and this one is slightly more complicated than the ones that you'll see in the homework, but I just want to give you a more complicated one to make the other ones feel a little bit easier. So here we have a survey that got sent out to 800 men, and all of them answered the survey. And they were asked to check the appropriate box or boxes in the following form. So they'll check off the first box if they're married. They'll check off the second box if they live in an apartment. Excuse me, if they live in an apartment. And possibly they're not married and they don't live in an apartment, so they wouldn't check either. Or possibly they're both married and they live in an apartment, and so they check both boxes, right? So they could check 0, 1, or 2 boxes in this survey. Okay, the results were tabulated as follows. 423 checked the married box, 386 checked the apartment box, and 197 were blank. So that's saying that they that neither one of these statements were true, so they didn't check either one of the boxes there. No boxes were checked. Okay, the first thing we'll recognize is our universal set here is the total amount of people that we were working with. And so the size of my universal set is going to be 800. Okay, and then we have 2 sets that we're working with. The set of people that are married and the set of people who live in an apartment. And I'll call those M and A. And we'll see what their cardinalities are, but we'll draw them here. Okay, and possibly they overlap or they don't overlap. If they don't overlap, the number that'll show up here is going to be the number 0. And so here we're given that 423 people checked the married box. So we know exactly 423 people are married. This is telling me that these two regions here should add up to 423 because both of them together give me back the total number of married people. So I don't immediately just write 423 here because I really want both of these regions. Okay, I also know 386 check the apartment box. And that 197 were blank. And so we'll have to decide what does that represent here. And actually something that we'll do before we finish this problem here, and I really should have put this in first, but we'll just do this now, is let's look at this Venn diagram here. And here we'll see if this box is representing my universal set, is I have 4 different regions showing up. I have this one outside, this one here, this third one, and this fourth one here. So when I'm working with 2 sets, I really have 4 regions that I'm working with, and I want to decide what are all of these regions. Okay, and let's actually start not with 1, let's start with number 2. What is this region here representing? This is representing the elements in A that are not in B, right? So I can write this as A minus B, or if I want to use my intersections and complements, this means in A and not in B. So A intersect the complement of B. So this is my and or my intersection, and this one really represents my not for my complement. Okay, number 3, this is actually a set that we've already talked about. This region here, this middle region, is what they have in common. It's going to be the intersection. Right? That's really the only way that, or the simplest way that we can write this. We don't really write this in terms of set minus because it's things in A and in B. Okay, next up, we have this region here in purple, which are the things in B that are not in A. So B and not in A. You can think of this as and this as not. Okay, and then the last thing that we're missing is our outside region. So let's use green for our outside region. These are all of the things outside of A. And they're also outside of B. Really, what we can see is that it's outside of the union of A and B here. Right? If I take A and B and I think about its complement, the things that are not inside of it, that's exactly what this region is representing. So I'll take A union B and I'll take the complement, and that's exactly the region on this outside here. So really, this is just to really emphasize is in our Venn diagram, we always have 4 regions. And whenever we draw up our Venn diagram and we want to write the number of elements in each, we're going to have one number inside of all these 4 regions. They should all add up to give us a universal set. And if I know what the size of A is, that's not enough to place it in this region 2. I know region 2 and 3 give me back A. So if I take region 2 plus region 3, oh, maybe I'll write it like this. And actually, our set A is really region 2 and region 3. Our set B is region 3 and region 4. Okay, and our union is region 2, 3, and 4. All right, but this really gives us the full scope of what's going on when we're working with 2 sets here. Okay, so let's go back to our problem, now that we kind of understand our Venn diagram a little bit better. Okay, so here, again, this is telling me that the number of people that are married, so the number of people inside of this set should total up to be 423, which is why I'm going to add up these 2 numbers together will give me back 423. Again, I cannot just write 423 here. This is technically the people that are married that don't live in an apartment, which is not necessarily 423. Okay, and we also saw we have 197 people left it blank, so they're not married and they're not living in an apartment, that's going to be this outside region, which is 197. And this really is representing the complement of the union. So if I think about the stuff outside of the union of M and A, this is going to give me back 197. Okay, the reason why this is so helpful is because this is really telling us how many elements do I have in my union. So my union here, the size of my union should be the universal set, the size of it, minus the complement of this set. So I should have 800 minus 197 because I really know the things inside my set plus the complement should add up to give me the full universal set here. Okay, and when I do this, I get back 603. So I know that the size of my union is 603. I know the size of A, I know the size of M. And so really the piece of information that's missing that's going to be the most helpful actually is going to be this region here, which is our intersection. So the and in A and M at the same time, the overlap. And I know how to count this through the calculations I did just earlier. I'm going to take the set A, count it, add it up to the number of elements in B, and subtract the number of elements in the union, which I have all of this information. This is really giving me back 386 plus 423 minus what's inside the union, which we just found to be 603. Okay, and when we do this, we get a total of 206. So I can now put this region here, the intersection of the two sets, what they have in common, as 206. I can also decide what is the size of this region here. This is the region M minus A. So things in M that are not in A. The way that I can find this is by looking at the total number of elements inside of M. So I have these two regions inside there, and I can subtract the intersection. This will give me just the things in M that are not in A. And I have this information now. This is 423 minus the intersection, which we found to be 206. And this gives me back 217. So I can now fill in this number to be 217. And the last piece of information that I'm missing is this one here, the things inside of A that are not in M. So A minus M. And here I can count up the total for A, but I want to delete the things that are also in M. So I'll delete M intersect A, and I have this info. This is 386 minus 206, which gives me a total of 180. Okay, and now I've accounted for all four regions. And as a sanity check, I can add up all of these numbers, and I can see I do get 800 as my total. So lots of times, the information that we're given is not directly what we can draw in our Venn diagram, but will help us to find those missing pieces. Okay, so we're going to use this information to help us to answer some questions, but we've really done the hard part right now by drawing the full Venn diagram. Now we're just deciding which pieces of it are representing the questions that we're asking for here. So here we want to ask, how many men live in an apartment but are not married? This is exactly asking for people in the apartment set and take away people that are not married. Or I can think in A and not in M. These are the same thing. This is exactly this region here in purple. This is going to be my 180. There are exactly 180 men who live in an apartment but are not married. If I want to decide how many men are married and live in an apartment, so here I'm seeing this and This is really representing my intersection. So married and live in an apartment. Or I can just look at my Venn diagram and decide which region am I talking about. And it's this overlap here, the things that they have in common, which is exactly 206 here. Okay, we could also have asked about the how many men live in an apartment or are married. And here, this or is an inclusive or. So it doesn't just have to be in one or the other. It's okay if it's in both. This is really the size of the union. And so I can add up all these pieces, the 217, the 206, or the 180. I actually already had this info too. This should give me back 603. But if I said something like how many men live in an apartment but are not married, or don't live in an apartment and are married, then I can just add up these two regions instead. But here, this or is inclusive. It's okay that there's, we count that the overlap here. So we do count all three regions there. But really, all of the hard work goes in drawing the Venn diagram and remembering that these regions here don't represent the whole M. It represents a piece of the M that's not, that does not overlap with A. So we want to be careful with that counting there. Okay, and the last thing we're going to do is we're going to look at an example where we have three sets showing up. And we're not going to fill in the full Venn diagram here, but we're just going to decide which piece of the Venn diagram are we working with because it's much harder to decide. We'll color in that region, and we'll also think about how do we write that in our set notation. Okay, so in the following example, we have 160 students complete a survey where they answered which one of the sports that they participated in high school. And the sports included basketball, soccer, and track. So B for basketball, S for soccer, T for track. And we want to indicate the regions that represent the following information. The actual numbers that are showing up here are not important, but we could use this to kind of help us fill in the full Venn diagram, but that's too complicated. We just want to figure out what are the regions that we're working with here. So here in this first one, we're working with students who participate in basketball and track. So I want them at the same time. This should be this specific region here, where B and T overlap with each other. This is their intersection. B intersect T, the overlap, right? Because we really want at the same time. We don't just want people that did basketball but didn't play tennis, or play tennis and didn't play basketball. We want them at the same time, students who played basketball and tennis. Okay, next up we have students who participated in basketball and soccer, but not in track, right? So if we just think about basketball and soccer, we'll have this region here. But we want to exclude the track students. So we're going to delete this region here. Okay, so this is the region of basketball and soccer students who did not play track or who were not on the track team. Okay, how we could represent this in our set notation. We want basketball and we want soccer. And at the same time, we don't want the track students. So again, remembering that this complement means not, and these intersections mean and. Another way that we could write this in terms of set minus is we're going to take the people who are in basketball and in soccer, and then take away set minus the track students, right? It gives us two different ways to do this. I feel like this one is the easiest to follow in terms of the words, in terms of changing ands and ors or nots, but they both represent the same set here. Okay, we want to represent, and maybe I'll just write these numbers here. In total, this is 25. In total, this is 25. Here we want to represent the students who participated, who did not participate in soccer. And it doesn't say anything about basketball or tennis. So really what we want is not soccer or the things outside of soccer, right? The complement which are not soccer. Okay, in terms of our set, it's going to be a pretty big region. Let's make this a little bit bigger. It's going to be everything that we see outside of our set S. So it can be students who are in basketball and track, but you just want to make sure that they're not in soccer as well. Or it can be students who are in none of them. In this full region, everything that I shaded in is going to be all worth 100 here. Right, so this information I can't use explicitly. I can't write it in my Venn diagram as one specific region. Really, I can see that this 1, 2, 3, 4 regions will add up to be 100. Okay, and we have one last one. We want the students that participate in exactly one sport. This is actually not that hard in terms of the Venn diagram, but in terms of writing it in our set notation, this is a lot harder to do. Okay, so here, if I want students that participate in exactly one sport, that one sport could be basketball. So I want them to participate in basketball, but nothing else. So I don't want any overlap with tennis or with soccer. Okay, that one sport could have been soccer though, but I don't want the students who did soccer and tennis or soccer and basketball. So just this region here with no overlaps. Or that one sport could have been tennis. So we want just this one region here. Okay, these regions combined give us the students that participate in exactly one sport, where we didn't clarify which sport it was. It could be any one of the three. If I want to write this nicely, or in terms of my set notation, this takes a lot of work. And so let's actually look at one at a time. How do we represent this region that's in B, but does not include S or T? So I want B, and I want to take away the things, or really I can think in B, and at the same time, it's not an S. And at the same time, it's not in T. Okay, so this is that one region that we have here. Okay, it can be in that region, or we can be in this region. So I'm going to put an or here, my union. And I'm going to decide, how do I write this portion? I can write this as in S, and at the same time, not in B, and at the same time, not in T. Okay, that's my whole set there. Or I can be in this region. So I'll put an or here. Right, this is representing or. I can play tennis, and at the same time, I don't want to play basketball, and I don't want to play soccer. So really, this is pretty complicated. And we can also do this in terms of set minus. Maybe I'll just write it for this region here. I can take the things in B and take away regions that overlap with S and T. So here I can take away my S union T. That would be another way that I could represent this region using set minuses instead of unions or intersections and complements here. All right, but the goal really is to try to understand what regions we're working with. And the hardest part is to write it in terms of the set notation, but hopefully thinking about it in the context will help you to translate. When you see an and, you use an intersection, an or will be a union, and a C or a not would be a complement here. Okay, but that's all we have for our sets. And you should see a homework assignment posted shortly after this video. Have a good one.